All right, peace, love, science, science. Huh. Funky, funky science. Oh, funky, funky, funky science. Yeah. Oh, funky, funky, funky science. Yeah. All right, peace. Gather round my children, pull up a chair, my friends. Let's all get together for the story that never ends. How do we get here? What's inside your head? What's bluer than blue? What's redder than red? Gather around my people, all children young and old. Pull up a seat, put up your feet for the greatest story ever told. Cause science is knowledge and knowledge is power. Because the world is so weird and weirdness is fun. And there's so much to learn and we've all just begun. Oh, we can learn together. We can understand the weather. We can imagine ourselves in outer space. We can see the earth from outer space. How? How do we do that? Oh, with science! Funky, funky science! Oh, funky, 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 funky science! Oh, funky, funky, funky science, yeah! Oh, we can learn together, we can understand the weather. We can imagine ourselves in any place. We can see the earth from outer space. How? Oh, with science! Yeah, a funky, funky science! Oh, science, science! Yeah, funky, funky science! Yeah, funky, funky, funky science, yeah! Yeah, with science! Oh, oh, funky, funky science! Hey, funky, 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 funky science, yeah! Oh, science, 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 funky science, yeah! Yeah! All right. Welcome to the Funky Science Story Hour. Now, please, please, please tell me that you can see and hear me. Also, the beard is amazing. Oh, I like that. Thank you. Thank you so much. Oh, it looks great. It sounds great. I'm not getting any panicky error messages this time that the audio's not working. So either you have all really become very, very, very good at reading lips, or I surmise, using my powers of deductive logical reasoning, that the audio is working. All right. Yes, this is as funky Science Story Hour can be, and I'm so happy to be here with you all again. And I, by the way, am David Grinspoon, aka Dr. Funky Spoon, and for the next 54 minutes I am going to share a little bit of science and music and fun with y'all. And it's great to be here. And I hope, I hope you're all safe and healthy and feeling okay. Heavy times right now, but we'll get back to that a little bit later. Right now, I just want to talk some science with you guys. Couple of things. If you comment, I can see the scroll coming by, and if you have a question, there's a little doohickey emoji thingy that's like a circle with a star in it. I think it's a purple star. Maybe one of the moderators can comment on exactly how you do that. But there's a symbol that you put at the beginning of a question, which alerts us to the fact that it is a question that you would like me to try to address. Hi, Liz Grinspoon. That is awesome. So if you got any questions, put the little circle in the star emoji thing. And by the way, this is part of CosmoQuest, the channel here on Twitch, which in addition to now hosting the Funky Science Story Hour every Wednesday afternoon at 3 p.m. Eastern, and whatever time zone you're on, wherever you are on this beautiful, crazy, mixed up world of ours, that's the time. But in addition to this show, CosmoQuest hosts a lot of really cool space and science shows. So take a look at, see that little purple star thingy? That's the thingy. That's the symbol. If you start your question with that symbol, then we know it's a question, and it draws our attention, and we go, hey, that's a funky science question to answer. Look, there's comments coming in here now on the scroll if you're new to Twitch, helping you learn how to do it. So pay attention to that. Thank you, moderators, for helping us out. And so check the schedule on the channel for CosmoQuest, because there's other really cool shows. There's a daily space update, and there's various other cool shows that get hosted that you should check out. And this is a product of the Planetary Science Institute, which is this really wonderful institute that I work with, and a lot of people do, that does a lot of science research, a lot of space research, but also some cool communication and outreach like this. Outreach. I'm reaching out to you. Give me 5. Don't knock over the laptop, though, in your enthusiasm. All right, so I want to talk a little bit more. I got some questions that came in about the Earth as a planet and kind of how it works, how it functions when you think of the Earth as a planet. There are some really distinctive things about the Earth that make it different from any other planet we know. When I say different from any other planet we know, keep in mind that we don't really know that much about most of the planets, right? We know a little bit about the planets in our own solar system that we are sending spacecraft to and discovering more. We just had a spacecraft go out to Pluto a few years ago, New Horizons. Actually, 5 years ago, this summer was the New Horizons flyby of Pluto, which brought home to us all the amazing pictures of Pluto. In fact, you can see my Pluto globe right there. See it? We couldn't have Pluto globes before 5 years ago because we had no idea what Pluto was like. So we know a little bit about the planets in our own solar system, and we know now that there are planets everywhere in the galaxy because we've discovered the exoplanets, the planets around other stars. So we know that there are planets around basically every star in the sky, which is an amazing thing to know, but we know almost nothing about them. We don't really know anything about those planets. It's very hard to investigate them because they're so small and so far away. They're small compared to stars and compared to the distances. They're not small from planets. Most of them are bigger than the Earth, most of those planets we've discovered, but they're really far away. So all we know about them is really how big they are and maybe how much they weigh, which tells us their their density. Maybe we know what they're made out of a little bit, but we don't know anything about their surfaces or their climates or anything. We know how far away from their stars. So when I say Earth is different from any other planet we know, keep in mind that in the history of learning about planets, we're at the beginning. We're at the very beginning. It was only, 1960. It was only really less than 60 years ago. No, less than 70 years ago. Okay. 1964. Yeah, less than 60 years ago that we sent the first spacecraft to another planet. There was a spacecraft called Mariner 2 that we sent to Venus in 1961. And that was the first ever spacecraft that was sent to another planet. And, that's pretty recent. So we've only started to learn about the planets, and we know very little about them. But we've examined most of the planets, really, the planets we know about in our own solar system. And there are some things about Earth that are very unusual, that we don't share with any other planet we know of. And one of the coolest things about Earth is something I want to tell you now about the way that the surface of the Earth moves around. And it's got a funny name, okay? It's called plate tectonics. That's a funny name, right? Plate tectonics. What does that even mean? Let me write that down for those of you that want to see. I'm going now to the super high-tech, funky science screen of knowledge here, okay? Plate, like a dinner plate. Like, hurry up and eat, your plate's getting cold. Or clean your whole plate off if you want to get dessert. Plate tectonics. Okay, it's a funny phrase, but it means something really cool. The word plate, you know what that means. It's like something thin and rigid that you could break into pieces if you're not careful, right? So, on Earth, the reason it's called plate tectonics is that the surface of the Earth, think of the whole round sphere of the Earth. The surface of the Earth is broken up into about a dozen, 12 or 13 rigid plates. Well, what do I mean by that? If you think of a plate, think of a dinner plate, and if you dropped it by accident, I'm not recommending that you do this experiment, kids, but imagine if you did drop it and it broke into shards, into pieces, right? And you'd be like, oh no, I wonder if I can glue this thing back together. You take all those pieces and you try to assemble them, and each of those pieces is rigid, but then there's cracks in between them. Well, it turns out that the whole surface of the Earth is like that. It's split into about 12 or 13 plates of rigid rock, okay? And those plates themselves are very rigid. They don't bend or move around very much, but they move around against each other. It's like bumper cars. They're sliding into each other and sliding over each other and sliding around each other. So picture the surface of the Earth as these about 12 or 30, that's about 12, about a dozen big plates that are all kind of sliding around and crashing into each other, doing bumper cars. That's what we call plate tectonics. The tectonics part, that's the plate is those rigid pieces of the Earth. Tectonics, that's just a funny word that means movements in a planet. Like when you get an earthquake, and parts of the planet are shaking and moving and sliding. We call that tectonic movement. So tectonics is just a funny word that means movement of parts of the Earth, moving around with respect to one another, pulling and sliding. That's tectonics. Plate tectonics is the fact that Earth's surface is split into these plates. Now, what's cool is that we haven't known this forever. In fact, I mentioned that history of when we started launching spacecraft to other planets in the early 1960s. At that time, we did not know how the Earth works. We didn't know about plate tectonics. It was only around 1970. So believe it or not, only about 50 years ago that we figured out how Earth works, really. And that's the theory of plate tectonics. And it turns out that almost all of the geological activity of Earth, and when I say geological activity, I mean the earthquakes, the volcanoes, the events that build mountains up, all the big geological events, they happen at the boundaries between those plates, where the plates crash into each other or pull past one another or pull apart or slide over and under one another. That's where all the geology, the action of Earth happens. Okay, so let me give you some examples. You've heard of the earthquakes out in California that happen once in a while. Maybe some of you live in California and you've felt those earthquakes. That's along a big crack in the earth that's called the San Andreas Fault. And that San Andreas Fault, well, there's other faults too. There's all kinds of faults along there. The San Andreas is just one of the big ones. But that's the boundary between two of these plates, these tectonic plates on the earth. There's the North American plate, which is most of California and going up to the West Coast, up to Oregon and Washington and back down to Mexico, down to the south. And then to the west of that, out over the Pacific Ocean, there's the Pacific plate. So there's actually a big crack in the earth right along near the west coast of California between those two plates. And those two plates are sliding, slowly sliding. One's pulling north and one's pulling south. And they stick. But once in a while, that force gets so that they pull past each other, and they're pulling and they're pulling and they're sticking. And then once in a while, the force gets so much that it goes and it slides. And that crack moves. And that's when you get those big earthquakes in California. When those two tectonic plates slide past one another. I was actually in one of those earthquakes. In 1989, I was in a big earthquake called the Loma Prieta earthquake that happened near San Francisco. And it was scary, man. I was inside this building working, and I was with a bunch of scientists, including some who study earthquakes, but when the building started shaking, it's like we're sitting there and it's like, what the heck? And it started rattling and crashing, and you could hear glass breaking, and it was really scary. And then when we got outside, you could see the trees moving. The trees were going like, and the cars in the parking lot were all going like low riders, except for they were doing it by themselves. It was pretty freaky. It's a powerful thing when the earth moves in an earthquake, and it's because two of those tectonic plates are sliding past one another. So that's one kind of interaction you can have where the two plates slide past one another. That's called a strike-slip motion, which is a fancy word for meaning place where the two plates are sliding past one another like that. But there's other kinds of boundaries between the plates too. A lot of times where we get the really high mountains on Earth, the highest mountains, like the Himalayas, or some people call it the Himalayas, or the Himalayas, in Asia, where Nepal and Tibet are, and Western China. And those really high mountains are because there are two plates moving towards each other and crashing into each other, and neither one is going to give, and so it squishes up. The Earth squishes up. So you actually have two plates that are slowly colliding and squishing up and making those really high mountains. Like the Himalayas are actually getting higher every year because those plates are actually still moving and squishing up the Himalayas. And by the way, when I say they're moving slowly, let's talk about how fast the tectonic plates move. They move about, on average, about 5 centimeters a year. So, or if you're used to thinking in terms of inches, 2 or 3 inches a year. About that far every year. And interestingly, That's the same speed at which your fingernails grow. So next time you're cutting your fingernails because they got a little bit too long, think to yourself, wow, my fingernails, they don't seem to grow very fast. On any given day, I can't really see them move, but I have to keep cutting them. So they're definitely moving over time. And that speed with which your fingernails grow is the same speed at which literally the ground of Earth is moving as those tectonic plates move around. Okay, so there's the kind of fault where two plates are sliding past each other, like in California, causing those earthquakes. There's the kind of boundary where two plates are squishing up into each other, causing big, big mountains like the Himalayas. And then, by the way, a lot of other mountains on Earth are places where that kind of activity was going on in the past, millions of years ago. So, like, if you live in the east coast of the United States, near where I am now, there are these mountains that go all the way up and down near the east coast we call the Appalachian Mountains. It's where the Appalachian Trail is. And those mountains are not as big as the Himalayas now, but a long time ago, a couple 100 million years ago, they were that big, because that's the site where a long time ago two plates crashed into each other. In this case, it was the North American plate and the African plate, believe it or not. Africa crashed into North America. It seems crazy, right? But if you look at the shape of the Atlantic Ocean, you notice that there's the two pieces. You take Europe and Africa, and then you take North and South America on the other side, and you notice how you could almost fit them together like a jigsaw puzzle? That's because actually in the past they were together, and they've crashed together and broken apart several times. And every time they crashed together, they built up big mountains. But it was a long time ago, so now those mountains have worn down by erosion. You have weather and wind and rainfall and vegetation wearing down those mountains. So the mountains are built up by plate tectonics, by the plates crashing together. And then over time, once that motion stops, they wear down by erosion on the Earth. And those plates do move around. And when I talked about Africa and North America crashing into each other, that's something called Continental Drift. Maybe you've heard of that, Continental Drift. It's pretty crazy, right? Because the ground seems very solid. It's like, well, I live on the Earth, and a lot of things in the world are uncertain and crazy right now, but at least you can count on the ground itself, the rock, being solid and doesn't move, right? Wrong. If you wait long enough, then the ground itself is moving, and the continents are drifting because of plate tectonics, because they're riding around on the rafts of these plates. Now, I'm going to tell you about one other kind of plate boundary. Okay, I'm going to tell you about two other kinds of plate boundaries, because it's cool. This is what unites all of geology on the Earth, this idea of plate tectonics. This is why it's cool. It literally is the unifying idea that makes us understand how all the different things are happening. Earthquakes in California, mountains in the Himalayas, volcanoes in Hawaii, you name it. It's all connected together by this motion on the Earth we call plate tectonics. Now, let's see. Okay, so there's one other kind of boundary I want to talk about. Sometimes two of those plates come together, but they don't squish up like that and make mountains like the Himalayas. Sometimes one of them will slide under the other one and dive deep down into the Earth. And when that happens, it makes a big trench in the bottom of the ocean. And it also squishes up volcanoes. Let me draw a little picture here, because this is cool. This is what we call subduction. It's kind of a funny word, subduction. But subduction is when one plate dives deep into the Earth under another plate. So, for example, this is the west coast of South America, okay? There's one plate here. This is where South America is. And then this is the Pacific Ocean. and it's coming in, the plate is coming in, and they're colliding, but the Pacific Ocean plate is diving underneath the coast of South America, way down. And when I say way down, I'm talking hundreds of miles into the earth that gets driven, because these two plates are crashing into each other. This one's moving this way, this one's moving this way, and something's got to give. So this one goes way down into the underneath the surface of the earth. That's what we call subduction. Sub means underneath, right? Like below. It's getting pulled down by subduction. And also this does a couple of things. One, the surface of the ocean here. Here's the surface of the ocean. And there's a deep trench. There's a deep trench. Some of the deepest water on the earth is right along the coastlines where you have this subduction. This is the trench in the eastern Pacific right by South America. But there's something else that happens that's cool. You know, you notice how, maybe you know this, that on the west coast of South America, there are huge volcanoes, some of the biggest volcanoes in the world. We call these the Andes Mountains, or the Andes volcanoes. And why are they there? It's because this rock is being subducted down into the interior of the earth. Remember, it's hot inside the earth. We talked about why that is in a previous Funky Science Story Hour, because of the radioactive decay inside of rocks. So rocks are heating up inside the earth. And so when this slab of rock of the ocean floor gets subducted, in this case beneath the coast of South America, it starts to melt. And as it starts to melt, then there's magma that starts coming up towards the surface. And this hot melted rock from down here where the subduction is happening squishes up and forms volcanoes. All these volcanoes along the coast of South America. Don't you love my artwork? So as this rock gets pulled into the interior of the earth, it starts to melt. The slab starts to melt and it squishes up and it comes out. Let me move Marcus Garvey here just a little bit. There you go. It squishes out into volcanoes, and those volcanoes, of course, release gas into the atmosphere, put in carbon dioxide, which changes the climate, and it affects a lot of things. Plate tectonics affects the geology of the planet, but it also affects the climate. It really connects everything. And one other thing I want to say before we maybe take a little musical break here on the Funky Science Story Hour is that this connects to something else that we talked about in a past episode. Remember we talked about convection in the interior of the earth? When you've got hot magma or hot rock inside of the earth, it rises up. And that's a convection current where hot stuff rises and cold stuff falls down. Kind of like the lava lamp. But my lava lamp isn't convecting now because I just turned it on recently. It's got to heat up and the bulb isn't hot enough yet. So oh yeah, we're back. Okay. You know what happened? I got so excited about my lava lamp that I literally pulled out my audio connector. You know, that's one of the problems with science, is that it's so exciting that, at least to me, that you can break things if you're not careful. So anyways, as I was saying, this lava lamp, this one right here, is not convecting now because it's not hot enough. It's like Mars or the moon, a smaller planet without enough heat in the interior, so you don't have that rising blobby hot rock and that falling blobs, those falling blobs of cold rock. Maybe later on in this Funky Science Hour, my lava lamp will start blobbing because I turned it on about half an hour ago and it's heating up. And if so, then it will change its behavior from Mars-like to Earth-like. But the point I'm trying to make here, I do have a point, believe it or not, and that's that it's that heat of convection inside the earth, and that motion of the rising of hot rock and the setting, the sinking of cold rock. That's what's pulling the plates around, okay? Because you can ask here, when I go back to this picture of subduction, why are these plates moving? What's pulling this plate inside the earth? And it's those big currents of rising hot stuff and sinking cold stuff, because there's heat inside the earth and the earth is convecting. It's kind of like it's kind of like a lava lamp. The earth you can think of as a heat engine. We call that a heat engine, where there's a source of heat and stuff is moving around. And that's causing all of these interactions on earth between the different plates. Just to recap, you've got the kind of motion where you've got earthquakes in California because two plates are slipping past each other. You've got the kind of motion where you've got mountains in the Himalayas rising up because two plates are squishing into each other and squishing up. You've got the kind of motion where you've got a trench and volcanoes in South America because one plate is getting pulled under another one deep into the earth and melting. And then there's one other kind of boundary I want to tell you about. It's called a mid-ocean ridge. And the mid-ocean ridges is where brand new plates are being made. So if you look at a map of the Earth's oceans, you know, you can see these cool maps now that show the floor of the Earth's ocean, the topography, the mountains on the bottom of the ocean floor. It's pretty neat. And one thing you'll notice is that in the middle of a lot of oceans, like in the middle of the Atlantic, there's a mountain range that winds all the way north to south in the middle of the Atlantic Ocean. And actually Iceland sits right on top of that mountain range. And we call that the Mid-Atlantic Ridge. And in general, there are ridges in the middle of all the major oceans of the Earth. And those mid-ocean ridges, that's where you've got that convection inside the Earth with the hot rock coming up. And it's got to go somewhere. And it comes out, there's a line of volcanic vents all along that mid-ocean ridge where new rock is coming out of the earth and forming brand new ocean floor. And those ridges are pulling apart. They're moving away from each other at, again, about 5 centimeters per year. So the same speed that your fingernails grow. And so you might ask, because you think about it, the surface area of the earth doesn't change. The earth isn't getting bigger and the earth isn't getting smaller, right? So if you've got places like this where ocean floor is being pulled into the center of the earth and is going away, if that was happening and there was not new surface being made, the earth would be shrinking, because here's ground literally going away. But it stays the same because there's new ground being created at the mid-ocean ridges. That's where the brand new floor of the earth, the brand new surface of the earth is being made at mid-ocean ridges. So that's another cool thing about plate tectonics, is that it's a way in which the earth's surface is always renewing itself. Because of that, the earth's surface is pretty young compared to any other planet we know, really, or almost any other planet we know. Like you look at the moon, or you even look at Mars, and you see these surfaces that are covered with craters. And that tells you these are ancient surfaces, billions of years old, where they've been getting hit by comets and asteroids, and those craters add up. Well, Earth is getting hit also by comets and asteroids over time, but you don't see it covered with craters because Earth's surface is always renewing itself. It's like Earth is getting paved over. You know how you get a road that's full of potholes, and then you're driving over it, and it's like, God, why don't they fix this road? And then one year they come along and they like repave it and it's all nice and smooth. Well, so Earth is always getting repaved by plate tectonics and by other things too, by weather and erosion. But that's a really cool and really unique thing about our planet. And it's not just cool and unique, but it's also one of the things that makes Earth such a good planet for life, because it's when plate tectonics happens and there's all these volcanoes and new rock coming up and old rock going down into the earth, it's recycling the minerals of Earth. It's bringing new minerals to the surface. And those minerals are a source of nutrients for life. and it helps keep the Earth refreshed. And those cycles of elements are one of the things that makes Earth such a great planet for life to exist. So plate tectonics is also something that really helps to keep the surface of the Earth fresh and alive, a good place for life. All right, I want to switch gears for a second and do a song. And the song I want to do today is by the great Bob Marley, Robert Nesta Marley, an amazing musician from Jamaica. Some people think he was a prophet. I just think he was a brilliant man and a genius musician, but he also had the ability to capture people's emotions and feelings, and he was a real strong spokesman for justice and peace in the world. And that's an important thing to think about right now. You know, one of the great things about science to me is the perspective it gives us of the whole Earth being united, right? You look at the Earth from space and you don't see boundaries and borders. You just see this beautiful blue ball of all these cycles of tectonics and weather and life. It's all united. And all the people on Earth are united too. When I think of the Earth from space and I think of the perspective of science, I think we are one human race, one human family. And I think that's an important perspective to have. And yet, as we know, this world we live in is also troubled, and there's racism and strife and violence sometimes, and people not understanding one another and not understanding that all human beings are important and worthy of love and respect. And so with that thought in mind, and just thinking of everything that's going on in the world, I wanted to, I just thought of playing this song, which is one of my favorite songs by the great Bob Marley. It's a heavy song. It's about slavery and the legacy of slavery and racism, which is a heavy, heavy, terrible thing in our society that we need to overcome. It's taken us way too long. And but it's also a song of freedom and hope and redemption. It's called Redemption Song. It's about moving forward and emancipating yourself from mental slavery. That, to me, that's the key line in the song. Emancipate yourself from mental slavery. It's about seeing things in new ways and overcoming destructive patterns of thought. To me, it's about seeing the earth whole and seeing humanity as whole, and looking at our history and saying, we can do better than this, people. Okay, I'm going to take this again, and hopefully the audio won't cut out. Oh, pirates, yes, they rob I. Stole I from the merchant ship. Minutes after they took I from the bottomless pit, but my hands were strong by the hands of the Almighty. We forward in this generation triumphantly. Won't you help to sing these songs of freedom? 'Cause all I ever had, redemption song. Emancipate yourself from mental slavery. None but ourselves can free our mind. Have no cure for atomic energy, 'cause none of them can stop the time. How long shall they kill our prophet while we stand aside and look? Some say it's just the heart of it. We got to fulfill the book. Won't you help to sing this song of freedom? 'Cause all I ever had, redemption song. emancipate yourself from mental slavery. None but ourselves can free our minds. Have no fear for atomic energy. None of them can stop at the time. How long shall they kill our prophet while we stand aside and look? Woo! Some say it's just a part of it. We've got to fulfill the book. Won't you help me sing these songs of freedom? 'Cause all I ever had, redemption songs, these songs of freedom. Redemption songs, these songs of freedom. Redemption songs. I think it worked. All right. Thank you for indulging me with that. But yeah. Anyways, this is one other thing I wanted to say. We only have about 10 more minutes now in this funky hour because I got to cut right at 4 today because they need the Twitch channel for another program. There's some days we'll be able to go a little bit longer. But the one thing, Lauren wants to know, what makes certain things poison? Oh, cool. Okay. Oh, that's a good question, Lauren. Yeah, I was gonna rap about the weather, but we'll get to that next time. What makes certain things poison? Yeah, good question. There's a few different things that can make something poison, but basically, the basic thing is that if you think about the way that our biology works, we talked about this in some past Funky Science story hours. You think about, inside your body, inside your skin or any part of your body, everything's made up of all these cells, these little tiny microscopic cells. And inside those cells, there are chemicals that are acting like a very finely tuned machinery, doing all the things that you need to keep living. So there are, we talked about proteins that are these long chain molecules, big carbon molecules with nitrogens and other things hanging off that are the kind of the building blocks of all the stuff in your body. And then the proteins also are they run the factories, the chemical factories. They bring other chemicals together so that things can react, and this is what we call your metabolism. Metabolism is just a funny word for all the chemical reactions that are happening inside you that keep you going. But basically, every one of those cells inside you is like a finely tuned machine of chemicals that are doing this dance, this complex dance, and interacting. And there are chemicals that are powering you, that are giving you energy. There are chemicals that are building up the structures of your body. There are, all these things going on. And if you think of it as sort of like a factory, then the poisons are like other chemicals that come in and sort of mess up the factory. They like come in, it's the wrong chemicals, and they either just sort of get in the way so that the good chemicals, the ones, the organic stuff inside you making you function, so that they can't work because there's other things in the way. Or some poisons actually break up the good molecules, the molecules that you need. They'll break up those proteins, or they'll break up the, remember we talked about DNA and nucleic acids, the chemicals that have the code that tell your body how to build other chemicals that you need. So there are, if something's a poison, it will come in and it will sort of screw up that machinery. it will break up the proteins or the other molecules inside you. When I say chemicals, molecules, it's the same thing. A molecule is just a kind of chemical. But the poisons will break up the molecules that you need, and so you can't function anymore, or they'll just sort of get in the way. But a poison is, there's different kinds of poisons, but what they all have in common is that they sort of get inside those chemical factories and they screw up the machinery. They get in the way of the chemicals trying to act in the right way to so that you can function well, or they break up the chemicals that you need. We could go into a lot more detail. There's a lot of different kinds of poisons, but the basic answer, Lauren, to your question of what makes something a poison is just that. Oh yeah, stay with us. This is important. I'm going to get off here in 5 minutes, but it says stay with us for coverage of the final press conference from the American Astronomical Society's virtual summer meeting. So if you guys are into brand new astronomy science results, then it's important, or you have the opportunity after I get off in a few minutes to get back on, to stay on this channel and watch that press conference with the hot new astronomy results. All right, well, I see we've only got 5 more minutes here. So I think I'm going to sort of bring this Funky Science Story Hour to a close. And I'm going to go out with the Funky Science Story Hour theme song, as we do. Somebody's saying here, one example is CO, carbon monoxide, or to a lesser extent, CO2, carbon dioxide. Hemoglobin hangs on to these more strongly than it does O2. Yeah, that's a great example. Okay, so hemoglobin in your blood that's the stuff in your blood. That's the stuff that makes your blood red, and it allows your blood to carry oxygen. There's a little slot in there. It's called a heme group. It's got iron and some organic molecules that carry oxygen in your blood. But if you've got carbon monoxide poisoning, carbon monoxide, CO, not CO2 like we've talked about. CO, carbon monoxide, is a poison. And the reason it's a poison is that your blood sees, the molecules, the hemoglobin in your blood sees that, and it thinks it's an oxygen. And it grabs onto the CO instead of the oxygen, and then your blood can't get oxygen. So you could asphyxiate. It's dangerous because you don't get the oxygen, because that simple molecule, CO, gets in there and blocks the oxygen. That's a really good example of the way a poison works. It just interferes with the machinery in that way. Okay, I got 3 minutes. I'm going to do a quick Funky Science Story Hour theme song, and I'll see you guys next time. Peace, love, and science. And thank you for bearing with me with the technical difficulties, but I think we're getting better. I think, science works by improvement. Our ideas are always getting better, peer review. We try something, and then we find out what's wrong. We get better. So this show's like that, too. So Funky Science Story Hour is always getting a little bit better. Peace, love, and science. Gather around, my children. Pull up a chair, my friends. Let's all get together for the story that never ends. How do we get here? What's inside your head? What's bluer than blue? What's redder than red? Gather around, my people, all children young and old. Pull up a seat, put up your feet for the greatest story ever told. Funky Science Story Hour, 'cause science is knowledge and knowledge is power. 'Cause the world is so weird, and weirdness is fun. And there's so much to learn, and we've all just begun. Oh, we can learn together, we can understand the weather. We can imagine ourselves in any place. We can see the earth from outer space. Oh, with science! Yeah, funky science! Oh, science! Yeah, funky science! Funky science, yeah!